The container management system Kubernetes was open sourced by Google with the intention of creating a cloud service based on the project. Today, the Kubernetes ecosystem is looking similar to the Android ecosystem, with different vendors providing different ways to use Kubernetes, from RedHat's OpenShift to Google's own container engine. Craig Mcluckie was a member of the team who originally devised Kubernetes, and he joins the show today to talk about the origins of Kubernetes and where the project is headed, exploring both the technical architecture and Google's business strategy around Kubernetes. Some quick announcements before we get started. The Software Engineering Daily community has started working on a project called softwaredaily.com. We are building an open source news and information site about software. This project is led by Jeff Tribble, and you can check it out by going to softwaredaily.com. We would love to have any help from any web developers out there. And you can also check out softwareengineeringdaily.com if you want to contribute as a host, or if you want to check out the Slack channel or my Twitter account or my email. You can also sign up for the Software Engineering Daily newsletter, Software Weekly, which features the content that the Software Engineering Daily team is checking out on a daily basis. And with that, let's get to today's episode, Kubernetes Origins with Craig Mcluckie. Everyone is talking about serverless architectures, and for good reason. It allows you to manage less infrastructure and deliver more results. At the forefront of this activity is the Serverless Framework, a popular open source application framework that makes it easy to build your serverless architecture on AWS, Microsoft, Google, and IBM. The team behind the framework has recently been funded by the investors behind Docker, New Relic, and HashiCorp, and they are looking for experienced, serverless-minded developers and evangelists to join them. If you have strong engineering experience with AWS Lambda, Elasticsearch, DynamoDB, and Redshift, or if you have experience building large, developer-focused communities, please go to serverless.com and apply. Let them know that you heard it from us, Software Engineering Daily. Thanks to Serverless for being a sponsor of Software Engineering Daily. We really appreciate it. And with that, let's get on with this episode of Software Engineering Daily. Craig Mcluckie was a member of the team who devised Kubernetes. Craig, welcome to Software Engineering Daily.
Thanks so much for having me.
Let's start by getting an origin story of Kubernetes. From your point of view, how did the earliest days of Kubernetes proceed?
So I'd be happy to share some of my experiences with Kubernetes. Just by way of background, I've been working at Google in cloud for about, 6 years now. And, previously I'd worked on a product which was called Google Compute Engine, which is a traditional virtual machine as a service offering. And I guess, Kubernetes really started coming about when a colleague of mine, a guy called Joe Bader, and I were working together on this VM-based product. And our very earliest experiences were kind of interesting in that we'd brought a traditional way of running enterprise workloads to this crazy sort of new age machine, which is Google's technical infrastructure. And one of the most marked things that we experienced was that our customers were really struggling to get the most out of our basic infrastructure. We would create these very pristine, very clean virtual machines, and they would buy them. And then we'd look at the utilization statistics, and they were only using a tiny fraction of the actual compute that they were effectively paying for. And so it was pretty clear that there was this jarring disconnect between the way that Google ran our workloads, which is really container packaged, dynamically scheduled, microservices oriented, versus the way that the world was running their workloads with virtual machine based, relatively static configurations. And so it was pretty clear right from our experience that there was this huge gap that existed, and we really wanted to start to fill the gap. And so Joe and I started thinking about what would the world look like if we could extricate some of the very best attributes of platform as a service, but make them available to people in a relatively accessible way, and really use some of the power of Google's infrastructure to the advantage of the enterprise customer. And around that same time, Docker started to emerge as a phenomenon. This was before it was very popular, but we were looking at a whole bunch of different technologies, and sort of Docker, piqued our curiosity as being something that we thought created this really elegant developer experience and solved a hard problem that developers had had for a long time, which is really the packaging and distribution of an application's components, so creating a static, hermetically sealed image that could be run. And so based on our experience with Google's infrastructure and experience building a VM-based offering, and with what we saw happening in the development community with Docker, it was pretty obvious to us that we needed to find this kind of glue that existed between the two worlds. And at that time, we had a third friend, a guy called Brennan Burns, who had sort of recently joined Cloud and was starting to experiment. And the whole thing started when we were talking to Brendan, and he wanted to do a demonstration for one of our internal all hands, and Brendan came up with this wonderful demo, which really felt like Borg, our internal system running on virtual machines. And at that moment, we all had this sort of epiphany that this was going to be the thing that we wanted to build. We wanted to create this Borg-like experience that stitched together a set of these very pristine and powerful virtual machines to create a logical computing fabric. And so we started talking to a variety of folks inside Google. We talked to Urs Horsley, who runs all of technical infrastructure. And we had this crazy idea, which is we wanted to build it in the open. We wanted to really create an open source project that brought this Borg-like experience to developers everywhere. And of course, Urs thought we were crazy. Why would we want to release it as open source, some of our most proprietary and most important technologies? And it took us a while to really kind of work through the thinking behind this, but it was pretty obvious to us because one is we saw open source as just being a far more powerful way of building technologies, and we were really impressed with the way.
So just to be clear, the plan was to first open source Kubernetes with plans to eventually turn it into a democratized cloud service.
That was the plan right from the get-go. So we really wanted to build it in the open, and it was kind of a first. No one had really built a cloud product in the open before. A lot of people had built cloud products around existing open source technologies, but we hadn't seen anyone actually start with open source and then turn it into a hosted product. And so that was a very different kind of pivot on how to build cloud products. And it was really important because we recognized the vast majority of our customers were actually running on-premise still. And that is true today. We're starting to see a transition where, in the next few years, the majority of workloads will be run in cloud. But the reality is most of our customers' first experience with this technology would be on-prem. And we knew that for us to be successful, we had to solve that problem first and then create a very effective hosted version of the technology that ran on our pristine infrastructure.
What are the advantages of knowing that you're going to be a cloud service from day one? Because there are plenty of products such as Hadoop or Kafka, these things that start as an open source project and then they get turned into a cloud service. But what are the advantages of knowing that from day one, this open source project is going to be turned into a cloud service?
It's interesting. The advantage in some regards, I think is not so much around the technical choices you make, though that is certainly true. One of the things we recognize is that because we wanted this to become a cloud service and because we expected other people to use it as a foundation for cloud services, multi-tenancy and isolation would be really important. And so we were able to bake in right from the get-go things like our namespace support, which is a really important consideration when you start thinking about these technologies as the underpinnings of cloud service and providing a hosting environment. But in many ways, we didn't want to get the cart ahead of the horse. We wanted to solve our customers' problems where those problems existed. And so we were quite fastidious about making sure that everything we did made sense on premise. And we definitely worked hard to ensure that customers could understand the value proposition of the technology where they were running it, and then that the translation later would happen sort of relatively effortlessly.
Why was the on-premise consideration so important? If you're eventually going to turn it into a cloud service and you're going to be vending it, why would it matter? Because if if you're not actually going to be having these on-premise users as customers?
The problem is that I actually experienced this pretty early on in my career here at Google, which is I'd sit down with CTOs of large financial service institutions or pharmaceutical companies and a bunch of other places, and a couple of things became very clear to me. The first is I had many people literally say to me, "You'll pry my data centers out of my cold dead hands." A lot of our early customers were hugely invested in at least having a story that let them benefit from their existing massive capital expenditure investments in on-prem data centers. And so very few of our customers were interested in a story that worked only on a single cloud. And the second thing that was clear is most of our customers didn't want to be in single cloud provider relationships. They wanted to have applications that they could run in different clouds, to increase the robustness of the availability, and just because they didn't want to be in a single provider relationship. And so it was pretty clear that if we pursued a strategy that only worked in our cloud, we would exclude the majority of our customers, because the majority of our customers wanted to have a technology story that spanned multiple clouds, including their on-prem data centers, and hybrid was such an important part of the narrative. And that's worked out really well for us. I don't think the product would have been successful if we had simply focused on creating the best rendition on Google. It's been successful because people are able to run it on premises, and then when they get to the point where they run out of capacity or they want to burst to the cloud or they want to try something different, it's very, very easy to take that application and then run it on our hosted version because it's literally the same code base.
Well, in the conversation around portability, that comes up a lot in the shows that I've done about Docker. What is the element of portability that Kubernetes adds that you do not get with just Docker, for example?
So Docker gives you the portability of an application component. So Docker creates this amazing, first 8 hours of experience with an application when you can take a base image, you can extend it, you can get it running on your laptop, and then you can get it running on the cloud. But the reality is, 80% of the cost of an application is incurred not during the development phase. It's actually incurred during the operations phase of the application. And so we weren't worried about just the first 8 hours. We were worried about the next 8 years when you're actually living with this application in production. How do you scale an application? How do you seamlessly upgrade an application so that it, without any form of interruption of service? How do you constantly monitor the health of an application, understand when something's gone wrong and seamlessly restart it without involving an operator? Those were the set of problems that Kubernetes was designed to solve. And it's not enough to just have the application pieces that can go from environment to environment. You also need the fabric that the application runs in, the fabric that thinks about your application and reasons about its health, reasons about its scaling processes, reasons about how to version it and update it, be as portable as the application itself.
Mm. So around the time that Kubernetes was created, there were some other cluster management tools like Mesos, for example. What was the state of other distributed systems management tools like Mesos? Did you take inspiration from these tools?
I certainly looked at tools like Mesos. At the time, there were a couple of technologies that were addressing some of these problems. And I did take a good, long, hard look at the relative technologies. And the two obvious ones were, I would say, Cloud Foundry and Mesos at the time. Cloud Foundry was written by Derek Collison, who was an ex-Googler. And it had solved some problems pretty well, but it had some issues that really, we looked at, what I looked at, and decided it wasn't going to address the core issues that we wanted to solve, particularly around stateful application management. The reality is that it works well for certain classes, the 12-factor application, but the reality is very few applications fit entirely into that mold. There's always some kind of stateful component. And most of the customers I talked to wanted a solution that would be holistic, that could solve all these problems. And when we looked at Borg, the internal cluster management system, everything runs in Borg. All of our stateful management sort of systems run inside Borg. So we knew it was possible, obviously, to create something that solved all those problems. I spent a lot of time looking at Mesos, and that was actually written by folks who had interned at Google. So it was also inspired by some of our internal systems. And the thing that kind of made me decide to do something net new was that, first of all, Mesos solved a specific problem, which is kind of a resource management, a resource assignment problem. But when I looked at the use cases, I spoke to a large number of systems integrators that actually were running Mesos deployments, read the code base, tried to really get a feel for it. There were two things that really held me back, or three things, I guess, that really held me back. One was it was a relatively large C++ code base at a time when Go was just representing a transformationally more powerful way to build these applications. I looked at it and I think about half the code could have been replaced by some of the core Go libraries. The second thing is that it really tended to think about your application as like your resources as a relatively static block. It was large, monolithic, required a very high level of operations overhead. I wanted something that was much lighter weight that could work well on 3 virtual machines and work as well on 3 virtual machines as it could on a 10,000 node cluster. So I really thought about this idea of a cluster as being something that you should be able to turn up with as little effort as you can turn up a virtual machine. And if you want to run multiple clusters, you should be able to do that. And Mesos was really more about just dealing with the basic resource management. But the final piece, and I think this is probably the most important, is that Mesos really didn't tackle a lot of the distributed systems problems that systems like Borg sort of deal with. Mesos provided a way to map a resource onto a physical machine, but it didn't think about how to tie applications together, how to create higher level primitives like services that would let you, piece an application together. So it was really limited to resource management, and most of the kind of distributed systems development happened at higher levels of the stack. So there were things like Aurora or Marathon or some of these other technologies. And, when I talked to a lot of our internal architects, they were reasonably convinced that, creating an artificial layer that separated the resource manager from the kind of application layer primitives would introduce some difficult sort of scheduling problems later that would make it more complex. And so we really wanted a lightweight, simple, portable system that provided an elegant set of distributed system primitives and that would be as easy to turn up as a virtual machine. And that led me away from Mesos and to actually doing something that new.
Okay, so let's talk a little bit more about the scheduler components, because in most of the conversations I have about Mesos or Kubernetes or other container management tools, distributed systems tools, the conversation turns to the scheduler. And on these different platforms, there are these different types of workloads that I need to schedule. So perhaps I have a user who is making a request to Gmail, and I need to spin up a container to serve that person a bunch of emails. This would be an unbounded job because the user, spins up a container, and from the point of view of the platform, you have no idea how long that job is going to run, how long that user is going to continue to make requests to that container. And then there's also these bounded jobs, like if a data scientist makes a request for a MapReduce job over 30 terabytes of data, that might take a while, but it's going to be a bounded job. It's going to have a fixed time, amount of time that needs to be spent on it. So when you were architecting Kubernetes, what were the big questions around scheduling that you were asking?
It's interesting. A lot of people have focused relentlessly on the problems associated with scheduling and building schedulers at scale. And to be honest, when we were looking at Kubernetes, and certainly for the first year, we instituted a radically simple scheduling algorithm. Like, we were not particularly worried about trying to get very fancy with scheduling because when I looked at what customers were actually using out there in the ecosystem, very few customers, and I use things like OpenStack as a kind of good starting point. For the first year of the project, the reality is most customers were not trying to build massive clusters. There were some set of customers. There were people like, the Twitters or the Netflixes or some of the really, forward-leaning folks that were really concerned about stitching together 10,000 machines to create a highly optimized compute fabric that could get 50% or better aggregate CPU utilization, but they were by far the minority of customers, and they were not representative of our target group, which is really the enterprise customer. Most of the enterprise customers were stitching together a small number of computers. They were looking to solve some basic problems around application lifecycle and productivity, etc. And so for the first year of the project, I literally was not that concerned about creating an optimal scheduling model. I was much more concerned about creating something that was accessible, simple, would scale to roughly 100 nodes, and would solve the problems that these folks had had for a long time, which is, how do I actually drive down the cost of operations for a modern application? Like, how do I get to something that, creates radical operational efficiencies for me? Because for those customers, the overarching driving cost wasn't so much the cost of the underlying compute, it was actually the cost of the operators and the developers. But at the same time, we recognized that, over the coming years, efficiencies would become a major, component. And I was very confident that we could build, efficient schedulers. Heavens knows a large number of people that have built, some of the world's best schedulers already work at Google, and they are working on the Kubernetes project. So I knew that was a problem we could solve. And so we just focused on making sure that the system was highly modular and was pluggable, and that we could over time introduce and refine and enhance the scheduler so that for given job types and other pieces we could make much more refined scheduling decisions. But it just wasn't that important for the first year because that's not where our customers were. The sweet spot customers, the enterprise customer.
What about the coordination story? Because in a lot of early Hadoop systems, you have a Paxos-based coordinator like Zookeeper, and later on you have Raft, and these distributed systems tools like Zookeeper, they're great, but they require this coordination, which can be computationally expensive. How much coordination is required in a Kubernetes cluster?
It's a great question. And this is, I think, one of the most essential kind of design decisions that we took. And there were two kind of parts of the inspiration here. We took inspiration from what we'd learned in Borg and its successor, Omega, in terms of how to actually structure the sort of control systems. There are certain functions that have to be centralized, and there are certain functions that you can afford to decentralize. And so we definitely took inspiration from the way that Omega was creating decentralized control systems. And the second thing is, Brendan Burns, who was one of the kind of key initial architects, was a robotics dude. He is a lot of his sort of education was in robotics. And so we spent a lot of time thinking about creating decentralized control systems. So there are a certain set of tasks that have to be centralized, and we looked at introducing a common control fabric. We basically used etcd to actually manage distributed state across the system. But wherever possible, we focused relentlessly on creating decentralized control systems. So, for instance, scaling operations on a set of pods, which is the kind of unit of deployment in Kubernetes, was handled by a replication controller. And the replication controller is responsible for controlling the replication of one set of pods, just one set of pods. It's not trying to look at and make replication decisions across the entirety of the cluster. So we'd stand up discrete replication controllers, and they would be control subsystems that would then look at the health of an individual subsystem within the cluster and make informed decisions about the management of that subsystem. And so wherever possible, we focused on decentralizing most of the control decisions and then creating a common control fabric for the things that couldn't be decentralized. So when a replication controller needed to allocate another pod, it would talk to a central scheduler that would then look across the pool of resources and make the allocation. It would then link the pod into would actually assign a label to it that would then link it into the control domain of that replication controller. But we were relentlessly focused on avoiding, wherever possible, centralized control models. And that has stood us in tremendously good stead. And it's the only practical way to build systems that are both scalable, but also have high levels of operations efficiency and very fast and low latency control decisions.
Does the user need to think about what aspects are centralized and what aspects might be have looser consistency, or is this mostly not in the purview of the user?
The user experiences this through the domain model. So the user doesn't need to think about this. There's, the way that you would, schedule a set of things is you create a replication controller, and that replication controller is then responsible for the life cycle of a set of things under management. So it does create, an onus on the user to understand how the control system works, and insofar as the user needs to understand what a replication controller is and what it does. But the user beyond that doesn't have to actually worry about, kind of trying to create an optimal architecture. The system itself, they tend to, fall into the trough of success in terms of, building distributed systems. There was always, what we were hoping to do is to make it easy to build highly scalable, highly manageable distributed systems by providing a rather opinionated way of thinking about things like control metaphors and the way that you tie things together with services and some of these pieces based on our own experiences.
I want to talk more about the intersection of Kubernetes and Google's cloud. We've done a lot of shows on the internals of Kubernetes, and I'm very curious about the process of productizing Kubernetes. So Google has this cloud service called the Google Container Engine. Can you talk about what Google Container Engine is and to what degree it is consuming Kubernetes?
Google Container Engine is literally a hosted version of Kubernetes. So it is the set of glue that's necessary to effortlessly turn up and manage a Kubernetes cluster. So there is some proprietary technology that's involved in provisioning and turning up and sort of managing the shape of a cluster. But under the covers, it's 100% open source Kubernetes code.
If you want to learn about Kubernetes, go to aprenda.com/sedaily. Today, you can find a webinar about Kubernetes, covering microservices, persistence, and multiple clusters. You can also find links to a past webinar covering the history, the origins, and the technical architecture of Kubernetes. The webinars at aprenda.com/sedaily are hosted by Joseph Jacks, a member of the Cloud Native Computing Foundation, who was previously a guest on Software Engineering Daily. If you're looking to move to a cloud-native infrastructure platform that works with your existing apps, you should also check out aprenda.com/sedaily. Aprenda provides cloud platform software that works with your existing applications and infrastructure. So if you're looking to migrate to cloud native, but you want to maintain your existing applications, you might want to check out Kubernetes and Aprenda. Thanks to Aprenda for being a sponsor of Software Engineering Daily. And if you want to learn about Kubernetes while supporting Software Engineering Daily, go to aprenda.com/sedaily. That's APPRENDA.com/sedaily. Thanks again, Aprenda. So the premise of this whole project has been that Google can run, Google, posits that we they hope they can run Kubernetes the best. Can you give me an example of what types of, obviously you can't talk in super detail about the proprietary stuff, but what are the areas of expertise that Google is focusing on to try to make this a competitively advantageous situation?
Yeah, it's interesting, and this really kind of derives from my experience with Compute Engine, and what went well with Compute Engine and what went badly. Google's infrastructure is amazing. It really is. It has some of the world's best physical infrastructure. Our network fabric is remarkable, and if I'd invite prospective customers to just try it. Profile it, compare it to other platforms out there. It has massive price performance advantages. The network latencies are spectacular. It uses our Google owned global network to connect to customers. There's just a lot of advantages in terms of the investments that Google's made in building and running our technical infrastructure at scale, and it's always been a really good product. But when we brought Compute Engine to market, our customer it wasn't enough, right? For a lot of customers, they were looking for more than just really wonderful physical infrastructure. They were looking for a story that worked on premises and in cloud. They were looking for a better set of ways to connect these things together. And so the premise behind Kubernetes is relatively simple. The first part of it is, look, it runs on Google's physical infrastructure, which was fine, high quality physical infrastructure. It just provides better bang for the buck, better aggregate performance. It's more consistent. We invite our customers to try it, and so that was a starting premise. It's just try infrastructure, you'll like it. If you run Kubernetes on-prem, your application will work effortlessly on our infrastructure, and we think you will find that it offers the best possible price performance and overall quality of service of any physical infrastructure out there available to you. The second part of it is that, as I looked at the way that we ran our infrastructure, so for instance, with Google Compute Engine, we tend to have these data centers that are relatively progressive. They're very modern. And so as part of Compute Engine, for instance, we always maintain and we aggressively update the underlying kernel of whatever we're running. And it's a very important part to maintain our security posture. And so we had to create live migration technologies so that we could move VM workloads around our data centers to meet our own internal scheduling decisions. So if you're running on a Google Compute Engine virtual machine, you can be pretty confident that you're running on a really secure base kernel. And we're, I think, one of the very, very few cloud providers that actually uses this sort of live migration technology to keep everything up to date. And so it was very hard for us to kind of build that in. Virtual machine workloads don't work all that naturally well with the way that we tend to schedule and build and run our systems. And so if we could get the world to move beyond the VM to actually get far closer to the way we run our workloads, our expectation is that over the next few years, we'll be able to provide even stronger cost advantages, radically better price performance over the workloads they see today as we get closer and closer to the metal.
I want to talk a little bit about the Kubernetes ecosystem. This is something I didn't really understand early on when I started doing shows about Kubernetes, but it's, initially I was like, okay, so this is a container platform and, it's just Kubernetes. I manage all my containers through it, but it's actually built to be quite modular, and there are projects that are already built on Kubernetes or that utilize Kubernetes as a component. There's RedHat's OpenShift, and there are also projects like Rancher that can use Kubernetes, or you can swap it out for Mesos or another container management tool. And this can be maybe hard to wrap your mind around. Like if you think about like a project like Ruby on Rails, there aren't multiple projects that people use to build and maintain Ruby on Rails projects. It's mostly like you use Ruby on Rails. Maybe you deploy Ruby on Rails to Amazon, or you deploy it to Google, or you deploy it wherever, Heroku. But it's not like you use Ruby on Rails as a plugin for some other component. So could you maybe like contrast like that ethos of Ruby on Rails with Kubernetes? Like how is it a component to be used as part of bigger projects?
This was a really important consideration as we entered into the system. When you think about it, we were looking to help the world transition from one style of infrastructure management to a new style of infrastructure management. Going from virtual machines to containers, going from statically scheduled to dynamically scheduled, going from maintaining an sort of implicit sense of who's talking to what to having explicit services, and formal microservice definition. So we were looking at doing something that was pretty bold, which is really helping the world go from this, let's call it a type 1, way of thinking about building applications to this type 2 model. And Google's not the only people that run type 2 clouds, right? So Twitter has co-evolved this with with the Mesos technologies. Netflix has co-evolved this. Facebook has co-evolved this with Tupperware. Like, each of these companies was independently, building out these types of systems. And, when we looked at the scope of what it takes to create an holistic Type 2 operating environment, it was breathtaking, right? There's obviously the underlying resource management pieces. There's the integration into the storage and networking ecosystems. There's the physical, application fabric. There's continuous integration systems that sit above it. There's, secret management technologies. There's this ocean of things you have to do that. And we knew this. I mean, we'd built one ourselves. And, as had Facebook, as had a number of people. But the reality is that when you think about like what really accelerates an ecosystem, you can, have a lot of commercial success if you create a relatively closed, vertically integrated ecosystem. But in our experience, open ecosystems are, far more powerful. And we didn't want to, try to create a story where everything you're running has to be Google provided. There's some things we'll do well, but we recognize that, if you look at, some of the things that are happening, look at like what Linkerd is doing with, proxy technologies, like it's pretty cool stuff. And our ambition was to move the world from Type 1 to Type 2. Our ambition wasn't to create a closed system to really own the Type 2 environment. Like at the end of the day, we're a cloud provider. We benefit when people run our infrastructure. And that means, creating a whole ecosystem of technologies that run our infrastructure. And so it was a safe bet for us to really focus on an open ecosystem. And I think it's played out incredibly well. I don't think we, go ahead.
It strikes me as very similar to the Android ecosystem, where you have different handset manufacturers that are trying to make the best Android phone. And, and then Google can look at those lessons and try to do the best they can also with something like Nexus.
That's exactly right. And, the intent here was to really foster an ecosystem and to empower an ecosystem and to enable an ecosystem. I truly believe that the transition from the Type 1 to Type 2 cloud is bigger than any one company. And
can you define that Type 1 to Type 2 cloud?
So let's say Type 1 cloud is a world where you're running in virtual machines. Your scaling event happens, on the order of, minutes, or on, compute engines, probably tens of seconds. You're running in a relatively statically sized container. You're responsible for the maintenance of your application. You have to upgrade it and deal with it yourself. It's relatively operation intensive, and most of the systems are monolithic. You don't get to kind of think about it as a sort of decomposed world. The Type 2 cloud is container packaged, dynamically scheduled, microservices oriented. It's what we call cloud native. It's a cloud native cloud.
Right. Okay. What about do you consider the serverless world? Is that going to be the Type 3 world?
It's an interesting question. I don't think that it's. I think serverless is an application pattern rather than a management pattern. You can absolutely build, and people have built serverless technology on a technology like Kubernetes, right? It's really about the shape of your application rather than the philosophy of your physical infrastructure management. So I don't think serverless is necessarily orthogonal. I think it's just a type of application or workload that fits very well into a dynamically scheduled world. Like it's characterized by dynamically scheduled, decoupled, etc. So I think it's just a form of this Type 2 application pattern that works really well for certain classes of workload.
So the dynamic scheduling, I would think of that as basically, I don't want to think about how my containers are scheduled. I just have my architecture set up to take care of that for me.
Yeah.
Okay.
I have a logical compute. Like instead of thinking about, I tend to think of this. In the old days, you'd have physical compute. You'd have this physical compute fabric where I deploy an application onto a physical machine. And the next stage was to create virtual compute, where I create a virtualized representation of a physical machine. I deploy my application into that. The third evolution of that is logical computing, where rather than having to worry about the physical shape of something, I request, computational resources. And it could be at the end of an event, in the case of, like a lot of these serverless computing paradigms, or it could be, I always want to have, precisely one of these things running, or it could be it scales up and down based on the shape of the workload, right? But it's deployed into a logical compute environment. I just throw a bunch of resources, into this logical compute environment. I create a technology that stitches it together and creates an application environment, and I can just drop applications into it.
And one logical extent of this is you get to usage of more platform as a service type of things, like Dataflow and TensorFlow are these Google's data processing and analytics solutions, which you can use as a service. Is that the natural extension of all of our application development? Am I going to be able to stop thinking of how much what size CPUs I need to provision for my Ruby on Rails application? I just say I've got a Ruby on Rails application. Hey, platform as a service, go figure it out.
Yeah, I think it's really a transition away from what I consider operator-driven applications to intent-driven applications, and I think it's a profound thing, right? An analogy I tend to use is, in the old days I used to have like one of these little model airplanes, and I guess it scarred my childhood because one day I was flying it over a sports field, and the next minute was 10,000 pieces of balsa wood lying across the sports field, right? Because they were really hard to fly, and it was an operator-driven thing. You'd use a control stick to do that. And today you have drones, and you provide a statement of intent. Hey, go there, go up, go down, do whatever. And there's some things that computers just do a lot better than people. And one of those things is controlling a little model aircraft or whatever it is. And this transition is as profound as the transition from a balsa wood airplane to a modern drone. By introducing intelligent control systems and introducing these patterns, the operator specifies their intent. I want this thing to return responses within 30 milliseconds, all the time. And the intelligent subsystems will observe what your latency is, and they'll make moment-to-moment decisions about how many front-end instances you need. They will observe every front-end instance, and they will decide whether or not it's healthy based on the pattern of the call patterns that it's generating, and they will restart the unhealthy ones and let you know that you've probably introduced a bug of some kind. It's profoundly different, and it's very powerful.
We did a show about the Google SRE role, which is kind of Google's flavor of the role of the operator. I'm sure Google has multiple types of operators, but to what degree is the SRE role enabled by a tool like Kubernetes?
That's a great question, and it's really kind of cutting to the heart of a lot of what this enables. When I think about one of the most profound changes that the technology like Kubernetes is going to introduce, and one of the profound changes introduced to Google is really enabling the specialization of operations, right? So we have this world we call DevOps today, which creates a situation where a developer, uses one set of coding tools to solve a business problem. Then they use a different set of coding tools to solve the problem of mapping that code into a physical environment and running it, right? And you're basically pushing a lot of the operations onus onto the developer. And the reality is, like, the way that a lot of people tend to think about DevOps is relatively inefficient. I speak to a lot of CTOs, and they use traditional configuration management, software, and they say things like, my ability to keep up is no longer based on the developer's ability to actually, code the business logic. It's actually based on the ability to, program the physical infrastructure that's getting deployed to. And so what we're likely to see, and what happened at Google, is that by introducing these technologies that create a logical compute environment, we were able to specialize operations. So infrastructure operations, the guys who rack and stack infrastructure and actually deal with the health of physical infrastructure, became a specialized thing. And they became very good at doing it. Cluster operations, the people that would stitch together physical infrastructure and create this logical compute environment, became another operations function. And then within that, we had different, folks that were operating common services, and they were specialized folks that were just delivering common services to all of our distributed systems developers. And then on top of that, you had the developers themselves that were building applications. And initially, they would run those applications and operate themselves, and then they would hand them off to an operations team. And so by introducing this technology that created this logical compute environment where you could take a developer's intent and run it, we were able to radically specialize our operations functions and create a far, far higher level of efficiency than we'd experienced previously.
So let's talk in more specifics. How does Kubernetes change the conversation around monitoring and security and other elements of the operations that are sometimes secondary considerations?
Yeah, it's pretty profound insofar as, today when you're a developer, you'll build an application and then you'll have to figure out like what is your logging story for that application. So I might use, hey, I'm a Java application, I use Log4j, and then I egress it to this, and then I have a bunch of other tools. And I pick up the set of tools that I want for my specific application, and I cobble together a whole application sort of management portfolio that includes monitoring, logging, backup, archival, etc. These all become things that I have to think about, and then I integrate them into my application environment and have to configure them along with my application itself, right? The difference is in a logical compute environment, you create common services that deliver those capabilities. And those services are available to all applications that are deployed into that cluster environment. So, for instance, you might have a service that provides log management. And it just shows up as a logging service inside Kubernetes that's directly discoverable. And you can introduce an agent into your application either as a little container in your pod that can then just integrate with that. But it talks to this common logging service. And so every application that's deployed into the cluster has access to one or more common logging services that are provided to them by a specialist operations team. They don't need to worry about configuring it and running it and deploying it into their environment. It just becomes a natural part of their compute ecosystem. And there's a specialized team that can actually provide that as a service to all of the application developers that are using that cluster. And so that sort of natural separation where logging just becomes an endpoint you talk to in the cluster environment. You don't know who's actually providing the logging service. You don't know what's behind it, but it's always there. That really changes the games for developers.
So what are the big challenges that are being worked on in the Kubernetes open source project right now?
So obviously, with 1.3, there's a few things that have changed. The first is, a relentless focus on increasing the set of workloads that we supported. So when we introduced Kubernetes, we were very focused on just providing a really elegant way to support stateless, web serving type workloads, and we did that pretty well. But obviously, as I mentioned earlier, most of our customers have some kind of stateful management, sort of requirements. And for Kubernetes to be a complete whole cloth management story, we need state management. And so, in 1.3, we introduced the pet set features, which is a state management solution, and that's an important consideration for the community. And over time, we'll expect to extend and enrich the set of workloads that we can support and make sure that we have really high quality pieces there. A second piece of work that we've been very focused on as a community has been around cluster federation. So a lot of customers want to deploy services into multiple availability zones, and they want to be able to address services independently of where they're running. And so we've put a lot of time and thought into stateful application management, and that's been an important consideration for the team. Beyond that, we're also focused on just continuing to drive and improve the overall fit and finish and quality of the product, making it easier to install on a variety of cloud environments, making sure that the community can scale. Like, it's a very big and very healthy and very vibrant community. We're putting a lot of time and thought into how to continue to enrich the community and scale it. We're thinking a lot about increased scale and automation. Like, how do we improve our ability to sort of automatically scale our clusters and automate the management of those clusters. So that just gives you a taste of some of the things that we're thinking about. But it's really about improving the story for the set of different workloads, increasing the number of workloads, making it easy to run clusters that are running in potentially sort of fragmented environments, and then just a consistent focus on the quality of the product, the ability to service the community, and just the overall experience of the product.
You are a product manager on Kubernetes, and we haven't done many shows on product management. I think of Kubernetes as a very unique project to be doing product management on. Can you tell me some about what your responsibilities are and how you fulfill them?
Sure. So I'm sort of a little bit unusual in terms of product management in that I tend to do the sort of I'm a sort of a natural incubator. So I build compute engine and Kubernetes and technological deployment management and a few of those things. So I tend to focus a lot on what's next and the community. My job has I think unlike a lot of other sort of traditional product management jobs is very, very focused on the community itself. So I spend a lot of my time working to make sure that Kubernetes is a great technology for the broader community and that the community owns the technology. So I started this project called the Cloud Native Computing Foundation, along with friends from Intel, RedHat, IBM, Cisco, VMware, etc. And so I'm sort of very outward focused on that. And then I tend to spend a lot of time thinking about what's next. How do we go beyond Kubernetes? How do we really enrich our story around services? What are the next set of things that are coming? So I manage a team of product managers, and my role tends to be sort of relatively evenly split between working to really engage the broader community of both customers and vendors who are betting on this technology, and then looking at helping the team to really evolve and create what's next for the community.
There were a few questions that you posed at last year's OSCON where you announced Kubernetes. And these questions were, what is the standard definition format for a distributed system? What is the profile of a basic computing node? I think you also asked, what are the common distributed systems services that developers bet on? And these are canonical questions. They're evolving questions. And I'm wondering how your answers to those questions have evolved in the last year.
That's a great question. Yeah, I'd forgotten I'd raised that to the community. I would say that I don't have the answers to those specific questions yet. I think that what we have done in the last year is to create the group that is actually going to ultimately answer this question. So, the last year for me has been spent on pulling together the Cloud Native Computing Foundation and working with a very engaged community of vendors to create the right sort of open, community-centric, kind of end-user-driven forum to really start addressing and answering those specific questions. So I don't think we're at a point where they're specifically answered, but I can say that I know who will ultimately answer those questions today, and that will be driven out by the Technical Oversight Committee of the Cloud Native Computing Foundation, with a lot of input from the growing end user community that's being germinated there.
Okay, well, that seems like a great place to stop. Craig, thanks for coming on the show. This has been a great conversation. I'm very excited about Kubernetes, and I'm pleased to continue reporting on it.
Thank you so much for your time. I really appreciate the opportunity to talk to you.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono.
Wow.